decades, the event horizon of a black hole was thought to be one of the most absolute structures in the universe. A clean boundary, a perfect edge, the final line where space, time, and information disappear forever. According to theory, nothing about it should change in any way we could notice. And yet, something is changing. In recent years, astronomers studying a supermassive black hole have observed behavior that should not be happening. Patterns of light near the event horizon are shifting. Magnetic structures appear to be reorganizing. The environment at the very edge of space-time itself no longer looks stable. What makes this unsettling is not just that the change exists, it's that no one knows why. The equations of general relativity still work. The black hole's mass hasn't changed. Its gravity remains the same. And yet the region where light is bent into a glowing ring, the last visible structure before nothingness, is behaving in ways our models did not predict. This isn't science fiction. This isn't speculation. These changes were observed by the same telescope that gave humanity its first direct image of a black hole. The event horizon is not supposed to evolve on human timescales, but it is. In this documentary, we will explore what scientists are seeing at the edge of a supermassive black hole, why these changes are so difficult to explain, and what they may reveal about physics under conditions that cannot be recreated anywhere else in the universe. We will look at magnetic fields twisting in extreme gravity, light behaving in unfamiliar ways, and the possibility that our understanding of black holes is still incomplete, not because our theories are wrong, but because they may be unfinished. This is the story of something happening where nothing should happen. The story of an edge that may not be as fixed as we once believed, and the quiet mystery unfolding at the boundary of space-time itself. If you enjoy slow, accurate journeys into the deepest questions of the universe, consider subscribing to Theories Before Sleep. Now, let's begin. For most of the history of modern physics, the event horizon of a black hole occupied a strange position in our understanding of the universe. It was not a place you could visit, not a surface you could touch, not even, in a practical sense, something you could see. It was a mathematical boundary, an invisible line in space-time defined by equations rather than observation. According to Einstein's general theory of relativity, the event horizon marks the point of no return. Once anything crosses it, light, matter, information, it can never come back. From the outside, the horizon should be simple, smooth, and unchanging, a perfect geometric consequence of gravity. For decades, that assumption went largely unchallenged. Black holes themselves were difficult enough to study. They emitted no light. They revealed their presence only indirectly through the motion of nearby stars or the glow of hot gas spiraling inward. The event horizon, by definition, was hidden. Then technology caught up. By the early 21st century, astronomers began building an instrument unlike any before it. Instead of a single telescope, they linked radio observatories across the entire planet, synchronizing them with atomic clocks. Together, these telescopes formed something the size of Earth itself. This was the Event Horizon Telescope. Its goal was audacious: to directly observe the region just outside a black hole's event horizon. Not the horizon itself. Nothing inside it could ever be seen, but the glowing ring of light created as matter and radiation are bent by extreme gravity at the edge. In 2019, the EHT succeeded. The image of the supermassive black hole at the center of galaxy M87 stunned the world. A bright ring, a dark center, a shadow cast not by an object, but by space-time itself. For the first time, the event horizon was no longer purely theoretical. It had an image. At first glance, that image appeared reassuring. It matched predictions. The ring size corresponded to the black hole's mass. The shadow aligned with Einstein's equations. General relativity passed another test. But science rarely ends with first impressions. As researchers continued to analyze the data, especially the polarization of the light forming that ring, they began to notice something unexpected. The structure around the event horizon was not static. Over time, the orientation of polarized light near the black hole appeared to change. Magnetic field patterns inferred from those measurements shifted direction. The environment near the event horizon was evolving. This was not supposed to happen. In classical models, the region near the event horizon of a supermassive black hole should be relatively stable over human timescales. The black hole's mass changes slowly. Its spin changes slowly. Its gravitational structure is fixed by geometry. And yet, the data suggested motion, reorganization, change. To understand why this matters, it's important to clarify what scientists mean when they talk about the event horizon changing. The event horizon itself, defined mathematically, is still governed by Einstein's equations. There is no evidence that the fundamental boundary has moved or violated relativity. The black hole has not shrunk or expanded dramatically. What is changing is the environment at the edge. The plasma, magnetic fields, and radiation just outside the event horizon, the only region we can observe, are behaving in ways that models struggle to explain. This distinction is subtle but critical. The horizon is a boundary. The edge is a system, and systems can be unstable. Near a supermassive black hole, matter does not fall straight in. It forms an accretion disk, a swirling superheated flow of plasma orbiting at relativistic speeds. Magnetic fields thread through this disk, twisting, reconnecting, and interacting with gravity in extreme ways. These magnetic fields play a central role in black hole behavior. They help regulate how matter falls inward. They extract energy from the black hole's rotation. They shape the enormous jets that shoot out from galactic centers at nearly the speed of light. In many theoretical models, these magnetic structures settle into relatively steady configurations, especially around massive black holes like M87 star. But the EHT data suggests otherwise. Between observations taken years apart, the polarization pattern near the black hole's edge appears to flip. The inferred magnetic field orientation changes. The structure reorganizes. This is not noise. This is not an artifact. Multiple independent analyses point to the same conclusion. Something dynamic is happening very close to the event horizon. The problem is that current simulations do not fully predict this behavior. General relativistic magnetohydrodynamic models, some of the most advanced simulations in astrophysics, can reproduce many features of black hole environments. They simulate plasma flows, magnetic turbulence, and relativistic effects. but the observed changes occur on timescales and in patterns that are difficult to reproduce consistently. This raises uncomfortable questions. Are our models incomplete? Are we missing key physics? Or is the behavior of matter near an event horizon fundamentally more chaotic than we assumed? One possibility is turbulence. The plasma near the black hole may be far more turbulent than previously thought. Magnetic fields may twist, break, and reconnect in complex ways, causing the observed polarization flips. Another possibility involves the black hole's spin. M87 star is rapidly rotating. That rotation drags space-time itself, a phenomenon known as frame dragging. This could interact with magnetic fields in ways that are not fully captured by current models, leading to evolving structures near the horizon. There is also the role of the jet. M87 star produces a powerful relativistic jet that extends thousands of light years into space. The base of that jet is anchored near the event horizon. Changes in magnetic fields at the jet's origin could reflect changes near the horizon itself. In other words, what we are seeing may be the black hole's engine adjusting itself. But even that explanation is incomplete. The most unsettling aspect of these observations is not that something is happening, but that it is happening on human timescales. Black holes are ancient objects. M87 star has existed for billions of years. Its mass and structure change slowly. To see measurable evolution over just a few years challenges intuition. It suggests that while black holes themselves evolve slowly, the environments they create can be dynamic, unstable, and responsive on surprisingly short timescales. This forces a re-evaluation of what we thought we knew. For decades, black holes were described as simple objects, defined by mass, spin, and charge. Everything else, the chaos, the radiation, the jets, was treated as secondary. The new observations suggest the opposite. The boundary region, the space just outside the event horizon, may be one of the most complex environments in the universe. Extreme gravity, extreme magnetism, extreme velocities, all interacting simultaneously, and we are only just beginning to see it clearly. This is why scientists are cautious. No one is claiming that relativity is broken. No one is claiming that event horizons themselves are dissolving or fluctuating wildly. What they are saying is more subtle and perhaps more profound. Our understanding of how matter, light, and magnetic fields behave at the edge of space-time is incomplete. The event horizon may be mathematically well defined, but the physics surrounding it is still being written, and that has consequences far beyond one black hole. If the environment near an event horizon can change in ways we don't fully understand, then black holes are not just passive endpoints of gravity. They are active laboratories of extreme physics, places where our best theories are pushed to their limits, places where new phenomena may emerge. In the next part, we will look more closely at how scientists actually detect these changes, how polarized light reveals invisible magnetic structures, and why those measurements are so difficult to interpret. Because the mystery does not lie in what we can see. It lies in what the light is trying to tell us. When scientists say they are seeing changes near a black hole's event horizon, they are not talking about photographs in the ordinary sense. They are talking about light that has been twisted, stretched, and polarized by some of the most extreme conditions in the universe. To understand why this matters and why it is so difficult to interpret, we need to look closely at how these observations are made and what they actually measure. The Event Horizon Telescope does not take pictures the way optical telescopes do. It does not capture colors or shapes directly. Instead, it records radio waves emitted by hot plasma orbiting near the black hole at nearly the speed of light. These radio waves carry hidden information, not just about where the light came from, but about the conditions it passed through. One of the most important pieces of that information is polarization. Polarization describes the orientation of light waves as they travel. Under normal conditions, light vibrates in many directions. But when light passes through strong magnetic fields, or is emitted by charged particles spiraling around magnetic field lines, those vibrations become organized. They align. In astrophysics, polarized light is a tracer of magnetic fields. You cannot see magnetic fields directly, but you can infer their structure by studying how they shape light. This is crucial near a black hole. Close to the event horizon, matter is not solid, liquid, or gas in the familiar sense. It exists as plasma, a soup of charged particles moving at relativistic speeds. Plasma interacts intensely with magnetic fields, and those magnetic fields control how the plasma behaves. They determine how matter spirals inward. They determine how energy is extracted. They determine how jets are launched. So when scientists analyze polarized light near a black hole, they are effectively mapping an invisible magnetic architecture. This is what the Event Horizon Telescope began doing after its first image. The 2019 image showed the shadow and ring. Later, analyses revealed something deeper, the polarization pattern of the ring itself. Those polarization lines appeared smooth and structured, suggesting organized magnetic fields near the event horizon. At first, this was exciting but not alarming. Many models predicted ordered magnetic fields in that region. The surprise came later, when scientists compared polarization data taken years apart. They noticed that the orientation of those patterns had changed, not slightly, substantially. The magnetic field structure inferred from the light appeared to flip direction. This raised an immediate question. What could cause such a change so close to the event horizon? At these distances, gravity dominates everything. Space-time is severely curved. Matter moves on trajectories dictated by Einstein's equations. And yet, magnetism is also present, and magnetism is messy. Unlike gravity, magnetic fields can twist, reconnect, and reorganize. They can store energy and release it suddenly. They can drive turbulence. The region near a black hole is where gravity and magnetism collide. Understanding that collision is one of the hardest problems in modern astrophysics. To make sense of the observations, scientists rely on simulations, specifically general relativistic magnetohydrodynamics, or GRMHD. These simulations attempt to model plasma flows and magnetic fields in curved spacetime. They are computationally expensive, complex, and still imperfect. GRMHD simulations can produce images that resemble what the EHT sees. They can generate rings, shadows, and jets. They can show magnetic field lines threading the disk and horizon. But matching a single image is not the same as matching evolution. The observed polarization changes imply that something dynamic is happening, something that evolves on timescales of years, not millennia. Some simulations do show variability. Magnetic turbulence can reorganize field lines. Accretion flows can fluctuate, but the scale and coherence of the observed changes are difficult to reproduce consistently. This leads to several possible interpretations. One is that the magnetic field near the event horizon is undergoing a process called magnetic reconnection. In reconnection events, magnetic field lines break and reconnect in new configurations, releasing energy in the process. This happens in the Sun's atmosphere, where it drives solar flares. Near a black hole, reconnection could be far more violent. If large-scale reconnection events occur near the horizon, they could reorganize the magnetic structure enough to change the observed polarization. Another possibility involves changes in the accretion flow itself. The amount of matter falling into the black hole is not constant. It fluctuates. Those fluctuations could alter how magnetic fields are dragged, stretched, and compressed near the horizon. Even small changes in density or velocity could produce noticeable effects in polarized light. There is also the role of frame dragging. A spinning black hole drags space-time around with it. This effect becomes extreme near the event horizon. Magnetic fields embedded in plasma are forced to follow the twisting space-time. If the black hole's spin interacts with the accretion disk in complex ways, it could cause magnetic structures to precess or reorganize over time. This introduces a subtle point. The event horizon itself may be fixed, but the space-time around it is not simple. It is dynamic, rotating, and interacting with matter. The observed changes may reflect not a violation of theory, but the full consequences of relativity playing out in an environment we are only beginning to resolve. Still, there is a deeper challenge. The EHT does not observe continuously. It collects data during specific observing campaigns, separated by years. This means scientists are seeing snapshots, not a movie. Interpreting change from snapshots is difficult. Are we seeing gradual evolution, sudden reconfiguration, or different states of an inherently chaotic system? Without continuous monitoring, these questions are hard to answer. Yet the fact that changes are detectable at all is remarkable. It means the region near the event horizon is not frozen in time. It is active, responsive, and possibly unstable. This challenges a long-standing intuition. Black holes are often described as simple objects, but simplicity applies to the interior and the horizon itself, not necessarily to the environment just outside. That environment may be one of the most complex natural systems in existence. Another layer of complexity comes from the fact that what we observe is filtered through extreme relativistic effects. Light near a black hole does not travel in straight lines. It loops around. It is lensed. Multiple paths can bring light from the same region to the observer. This means that the polarization pattern we see is a composite of many paths, many interactions, and many distortions. Small changes near the horizon can be magnified in the image. Interpreting polarization in this context requires care. A change in observed polarization does not map cleanly to a simple change in magnetic field orientation. It is a convolution of physics and geometry. This makes the mystery deeper, because even after accounting for known effects, the observed changes remain difficult to explain fully. Scientists are not panicking over this, but they are paying attention because black holes occupy a unique position in physics. They are places where gravity is strong. quantum effects may become important, and classical descriptions begin to strain. If something unexpected is happening near an event horizon, it could be a clue, not to a failure of relativity, but to physics we have not yet fully explored. It could tell us how magnetic fields behave in extreme curvature. It could reveal new plasma instabilities. It could expose limitations in our simulations, or it could point toward deeper connections between gravity and other forces. At this stage, caution dominates interpretation. The phrase "scientists don't know why" does not mean scientists are confused or lost. It means the data is ahead of theory. This is how progress usually happens. Observation reveals behavior. Models attempt explanation. Gaps are identified. Understanding evolves. The event horizon is not changing in the sense of violating known laws, but our picture of what happens around it is changing. And that shift matters, because black holes are not rare. They sit at the centers of galaxies. They influence star formation, galactic structure, and cosmic evolution. Understanding how they interact with matter and magnetic fields is essential to understanding the universe at large. In the next part, we will look at the specific black hole involved, M87*, and why its size, spin, and jet make it a uniquely powerful laboratory for studying these mysterious changes. Because the story is not just about light and magnetism, it is about scale. At the center of this mystery sits a single object, vast, ancient, and almost incomprehensibly large, the supermassive black hole known as M87*. It is not just another black hole. It is one of the most extreme objects ever studied in detail, and that extremity is precisely why scientists chose it as their first target. M87* resides at the heart of the giant elliptical galaxy, Messier 87, roughly 55 million light-years from Earth. Its mass is estimated at around 6.5 billion times that of the Sun. That number is difficult to grasp, but its consequences are easier to describe. The larger a black hole is, the slower everything around it evolves, at least in relative terms. For stellar mass black holes, changes near the event horizon happen too quickly to image clearly. Matter falls in, magnetic fields twist, and structures rearrange on timescales of seconds or minutes. M87* is different. Because it is so massive, time near its event horizon stretches out. Orbital periods are longer. Plasma flows evolve more slowly. Structures persist long enough to be observed. In other words, M87* offers something incredibly rare, a black hole whose edge evolves slowly enough for human instruments to track. That makes it a natural laboratory for studying extreme gravity. But M87* is remarkable for another reason. It launches one of the most powerful relativistic jets ever observed. This jet extends thousands of light-years into space, blasting out streams of charged particles at nearly the speed of light. It is so bright that it was visible long before the black hole itself was imaged. For decades, astronomers studied the jet without being able to see the engine that powered it. Now they can, and that connection between the jet and the event horizon is central to the mystery. Jets do not form randomly. They require strong, organized magnetic fields. They require rotation, and they require matter interacting with space-time in just the right way. The leading explanation is known as the Blanford-Znajek mechanism. In this model, magnetic field lines anchored in the accretion disk and threading the event horizon extract energy from the black hole's spin itself. If this mechanism is correct, then the magnetic fields near the event horizon are not passive features. They are structural. They are part of the engine. This means that any observed change in magnetic field configuration near the event horizon could have consequences for the jet and vice versa. So when scientists saw polarization patterns near M87* change, they immediately asked, is the engine adjusting? One possibility is that the black hole has entered different magnetic states over time. Some simulations suggest that black hole accretion systems can flip between regimes, sometimes dominated by orderly magnetic fields, sometimes by turbulence. These states can affect how efficiently energy is extracted and how jets behave. In such a scenario, the event horizon region itself may remain geometrically stable, while the magnetic scaffolding around it rearranges. That would explain why relativity still works, but the light changes. But there is a complication. The jet from M87* appears remarkably stable on large scales. Its direction does not wander significantly. Its structure remains coherent over long periods. If the magnetic field near the horizon were undergoing violent reconfiguration, wouldn't the jet respond? Not necessarily. The base of the jet, the region closest to the black hole, may be more dynamic than the jet further out. Changes near the horizon could be damped as they propagate outward, preserving the jet's large-scale appearance. This introduces a layered picture. The farther you are from the black hole, the more stable things look. The closer you get, the more volatile the environment becomes. This makes intuitive sense. Gravity is strongest near the horizon. Space-time curvature is most extreme. Magnetic fields are compressed and twisted. Plasma densities are highest. If instability exists anywhere, it would exist there. Another factor that makes M87* uniquely valuable is its orientation. From Earth, we view M87* at a slight angle rather than directly edge-on or face-on. This gives us a clear view of the shadow and ring structure, as well as the jet emerging upward. This geometry helps scientists disentangle different effects. They can distinguish between changes caused by rotation, viewing angle, and intrinsic evolution. Even so, the picture remains incomplete because M87* exists in an environment shaped not just by itself, but by its galaxy. Messier 87 is a massive galaxy embedded in a dense cluster. Gas flows toward the center from large scales. That inflow may not be steady. Variations in supply could ripple inward, eventually reaching the event horizon region. This raises an important point. The black hole does not exist in isolation. It is connected to its galaxy across enormous distances. Small changes far away can propagate inward over time, influencing what happens at the edge of space-time itself. In this sense, the event horizon is not an isolated boundary. It is the deepest point in a much larger system. That system includes galactic gas flows, accretion disk dynamics, magnetic field amplification, relativistic frame dragging. All of these factors interact. When scientists say they do not know why the event horizon environment is changing, they are not admitting ignorance of basics. They are acknowledging the complexity of coupling across scales. Understanding M87* requires bridging physics from thousands of light years down to fractions of a light hour. That is an extraordinary challenge. Another reason M87 star matters is comparative. The EHT has also imaged the black hole at the center of our own galaxy, Sagittarius, a star. Sagittarius A star is far smaller, about 4 million solar masses. Its environment evolves much faster. Its images change dramatically over short periods. In contrast, M87 star was expected to be calmer. That expectation is now under scrutiny. If even a black hole as massive as M87 star shows unexpected variability near its event horizon, then dynamic behavior may be universal rather than exceptional. This has consequences for how we interpret all black hole images. A single snapshot may not represent a stable state. It may capture one moment in a shifting configuration. That realization changes how certainty must be framed. Black hole images are not portraits. They are frames from a film we are only beginning to watch. M87* also forces scientists to confront the limits of symmetry assumptions. Many models assume axial symmetry, smooth, circular structures around the black hole. Reality appears messier. The polarization data suggests asymmetry, preferred directions, evolution. This messiness is not a flaw. It is a clue. Nature rarely arranges itself into perfect symmetry unless constrained to do so. Black holes are constrained by gravity, but not by magnetism. The magnetic environment can break symmetry, introduce structure, and drive evolution. And that may be what we are seeing. Still, caution remains essential. The EHT is pushing technology to its limits. Extracting polarization signals at this resolution is extraordinarily difficult. Calibration errors must be ruled out. Instrumental biases must be understood. Scientists are careful not to overinterpret, but they are equally careful not to dismiss. Because even after accounting for known uncertainties, the pattern remains. Something is evolving near the event horizon of M87 star. Not explosively, not catastrophically, but measurably, and that alone is enough to demand attention. M87 star teaches us that black holes are not merely endpoints. They are ongoing processes, engines embedded in cosmic systems, and their edges, once thought to be static mathematical boundaries, are surrounded by environments that live, shift, and respond. In the next part, we will step closer still. We will examine what these changes might mean for the deepest foundations of physics, whether they challenge relativity, hint at quantum effects, or simply reveal complexity we underestimated. Because when observations reach the edge of theory, even small anomalies matter. As the evidence accumulates, a deeper and more unsettling question begins to surface. What if the changes we are observing near the event horizon are not just complications of plasma physics or magnetic turbulence? What if they are telling us something fundamental about the nature of space-time itself? This is where the discussion becomes delicate, not because scientists believe Einstein was wrong, but because even Einstein's theory was never meant to be the final word. General relativity has passed every test thrown at it for over a century. It predicts black holes with astonishing accuracy. It explains gravitational waves, time dilation, and the bending of light. The size and shape of the black hole shadow seen by the Event Horizon Telescope match its predictions. almost perfectly. And yet, relativity is incomplete. It does not include quantum mechanics. It does not explain gravity at the smallest scales. It breaks down at singularities. Black holes sit precisely at the intersection of these limitations. For decades, physicists assumed that whatever new physics exists near black holes would be hidden behind the event horizon, forever inaccessible to observation. The horizon was thought to act like a curtain, sealing off the unknown. But the new observations complicate that assumption, because while we cannot see inside the event horizon, we can see extremely close to it. And if the environment just outside is behaving in unexpected ways, it raises the possibility that subtle effects of deeper physics might be leaking outward, not directly, but indirectly. This does not mean the event horizon itself is dissolving or fluctuating wildly, but it does mean that the clean separation between known physics outside and unknown physics inside may be blurrier than once thought. One place this tension becomes apparent is in the behavior of magnetic fields. In classical physics, magnetic fields evolve according to well-understood equations. In relativistic plasmas, those equations become more complex, but still, in principle, predictable. Yet near an event horizon, space-time is so strongly curved that even defining what a field line means becomes tricky. Coordinates stretch, time dilates. Different observers disagree about what is happening simultaneously. Under these conditions, magnetic fields may behave in ways that defy intuition developed in flatter spacetime. The polarization changes observed near M87 star could be a manifestation of this. Not new forces, but familiar forces pushed into regimes we have never tested directly. Another theoretical frontier involves causality. The event horizon defines the ultimate causal boundary. Inside it, events cannot influence the outside universe. Outside it, physics should remain well behaved. But the region just outside the horizon is extreme. Signals are delayed. Time appears to slow. Paths of light loop and overlap. Small perturbations in this region can have outsized observational consequences, because light can orbit the black hole multiple times before escaping. This creates echoes, overlaps, and interference patterns that can amplify subtle changes. In such an environment, even minor shifts in plasma flow or magnetic orientation could appear dramatic in the final image. This raises a key question. Are we observing fundamentally new physics? Or are we seeing classical physics magnified by extreme geometry? At present, scientists lean toward the latter, but the distinction is not trivial, because even if no new physics is required, our ability to predict behavior in this regime may still be limited. This brings us to another theoretical challenge: chaos. Chaotic systems are deterministic but unpredictable. Tiny differences in initial conditions grow exponentially over time. Long-term prediction becomes impossible, even though the underlying laws are known. The environment near an event horizon may be chaotic in precisely this sense. Plasma turbulence, magnetic reconnection, relativistic motion, and curved spacetime all interact non-linearly. Small fluctuations could cascade into large-scale changes in magnetic structure. If this is true, then the changes observed by the EHT may not signal a specific cause, but an inherent unpredictability. This would mean that the region near a black hole's edge is not just extreme, but fundamentally sensitive. and that sensitivity would place limits on what we can ever predict, no matter how good our models become. This idea is uncomfortable for theorists. Physics prides itself on predictability. Chaos challenges that pride. But chaos does not imply randomness. It implies complexity beyond simple forecasting. Another area where theory strains is in the relationship between the event horizon and the membrane paradigm. In some approaches to black hole physics, the event horizon is treated as if it were a physical membrane with properties like conductivity and viscosity. This is not literal, but it is mathematically useful. In this framework, magnetic fields interacting with the horizon behave as if they are anchored to a surface that can twist and respond. Changes in polarization patterns could be interpreted through this lens, not as the horizon changing, but as the membrane responding dynamically to its environment. This interpretation preserves relativity while allowing for richer behavior near the boundary. But even here, the membrane paradigm is an approximation. It does not emerge from a full theory of quantum gravity. It is a tool, a bridge between classical intuition and relativistic reality. The deeper question remains unanswered. What is the true microscopic nature of an event horizon? Is it smooth? Is it structured? Is it purely geometric? Or does it encode information in subtle ways? Some theoretical proposals suggest that horizons may have quantum hair, small deviations from perfect smoothness that could, in principle, influence nearby physics. Others argue that horizons remain classical until probed at scales far smaller than we can observe. The current observations do not resolve these debates, but they sharpen them because they demonstrate that the region near the horizon is not as quiescent as once assumed. There is also the issue of information. Black holes famously raise the information paradox. What happens to information that falls in? Does it disappear? Is it encoded on the horizon? Is it preserved in subtle correlations? While the EHT observations do not directly address this paradox, they touch adjacent territory. If the environment near the horizon is evolving in complex ways, it may influence how information is scrambled, mixed, or imprinted on outgoing radiation. This does not mean information is escaping, but it does mean the boundary between inside and outside may be more active than previously thought. Once again, caution is essential. No observation so far violates general relativity. No data demands exotic explanations. But history shows that new regimes often reveal surprises. When Mercury's orbit deviated slightly from Newtonian predictions, it did not overthrow gravity, it refined it. When blackbody radiation resisted classical explanation, it did not abolish physics. It led to quantum mechanics. Small discrepancies matter. They point to edges where understanding transitions. The event horizon is the ultimate edge. Another important theoretical implication concerns universality. If the observed changes near M87 star are intrinsic to black hole environments, then similar behavior should occur around other black holes, regardless of size. The difference would be timescale. For stellar mass black holes, changes might occur too rapidly to observe directly. For supermassive black holes, they unfold slowly enough to catch. This suggests that black hole edges everywhere may be dynamic systems, not frozen boundaries. And if that is true, then textbooks describing black holes as simple objects need revision. The simplicity applies to the interior description, mass, spin, charge, but not to the surrounding physics. The horizon may be simple, the edge is not. This distinction may become one of the defining insights of modern black hole astrophysics. Not that black holes are changing in forbidden ways, but that our mental picture of them was incomplete. They are not silent voids with passive surroundings. They are active participants in their cosmic environment, engines where gravity, magnetism, and motion interact continuously. As theoretical work continues, scientists are refining simulations, exploring new regimes, and preparing for better data. Future versions of the event. Horizon Telescope will have higher resolution, more observing sites, and more frequent monitoring. Instead of snapshots, we may eventually see sequences, patterns of change, cycles. Only then will we know whether the observed evolution is episodic, periodic, or chaotic. For now, the safest conclusion is also the most profound. The event horizon itself remains intact, but the region around it, once assumed to be static and predictable, is alive with complexity. And that complexity sits at the boundary of what we understand. In the next part, we will explore what this means for the future of black hole observation and how upcoming instruments may finally turn mystery into measurement. Because when theory reaches its limits, observation becomes the guide. The realization that something near the event horizon is changing does not end the story. It opens a new one. Because once scientists accept that the edge of a black hole is not observationally static, the next question becomes unavoidable. How do we watch it evolve? Until now, black hole studies have been dominated by single moments, snapshots captured at the limits of technology. The first image of M87 star was historic, but it was also incomplete. It showed structure, not motion, shape, not time. The recent polarization changes hint that time itself must now become a central variable in black hole astronomy, and that shifts everything. The Event Horizon Telescope was never designed to be a continuous observer. It relies on synchronized observatories scattered across the Earth, operating together during limited windows each year. Atmospheric conditions, funding cycles, and logistical constraints all limit how often it can observe. This means that the changes detected so far are glimpses, not narratives. And yet, even those glimpses are enough to suggest that the region near the event horizon may undergo cycles, perhaps subtle, perhaps violent, that unfold over years or decades. To understand such behavior, astronomers are now rethinking how black holes should be monitored. The goal is no longer just to image a shadow. It is to track a living system. One major step in that direction is expanding the Event Horizon Telescope itself. New observatories are being added in strategic locations to increase resolution and coverage. More baselines mean sharper images. Better coverage means fewer gaps in interpretation. With these upgrades, future observations will be able to resolve finer details in the polarized light near the horizon, and do so more frequently. Frequency matters. If the magnetic field structure near M87 star flips direction over several years, scientists need to know whether this is a one-time transition or part of a repeating cycle. Is the system oscillating between states? Is it drifting toward a new configuration? Or is it behaving chaotically with no long-term pattern at all? These questions cannot be answered with isolated data points. They require time series observation. Another promising development involves combining EHT data with observations at other wavelengths. Black holes emit across the electromagnetic spectrum. X-rays reveal high-energy processes near the accretion disk. Optical and infrared light trace larger-scale gas flows. Radio waves map jets extending far from the core. By correlating changes seen in polarized radio light with activity in other bands, scientists can look for cause and effect relationships. For example, if polarization changes coincide with flares in X-rays or shifts in jet brightness, that would suggest a connection between magnetic reconfiguration near the horizon and energy release farther out. This multi-messenger approach transforms black hole study from isolated imaging into system-level analysis. But even that may not be enough. Some of the most interesting physics near the event horizon may occur on timescales shorter than current observations can resolve. To capture those dynamics, astronomers are exploring the possibility of space-based interferometry. Putting radio telescopes in orbit would extend the effective size of the EHT beyond Earth itself. Longer baselines mean finer resolution and potentially more frequent coverage. Such missions are technically challenging and expensive, but the payoff would be extraordinary. For the first time, humanity could watch the edge of a black hole evolve in near real time. This would not just refine existing models, it could overturn them. Because once motion is observed directly, ambiguity shrinks. At the same time, theoretical work is racing to keep pace. Simulations are being pushed to higher resolution, longer durations, and more realistic conditions. Instead of modeling idealized disks and magnetic fields, scientists are incorporating turbulence, variability in inflow, and more complex plasma behavior. These simulations are not meant to predict exact outcomes. They are meant to map the space of possibilities. What kinds of magnetic evolution are possible near an event horizon? What timescales are natural? What patterns repeat and which do not? Answering these questions helps scientists recognize meaningful signals in observational data. Another frontier lies in machine learning. The data produced by EHT observations and simulations is immense and complex. Subtle patterns may be difficult for humans to identify directly. Machine learning algorithms can be trained to recognize characteristic signatures of different physical processes: magnetic reconnection, turbulence, frame dragging effects. These tools do not replace theory, they augment it. They help guide attention to features that deserve closer scrutiny. Yet even with better data, better simulations, and better analysis tools, some uncertainty will remain. That is not a failure. It is a feature of studying nature at its extremes. The region near an event horizon is not just extreme in gravity, it is extreme in information density. Many physical processes overlap. Many effects mimic one another observationally. Disentangling them requires patience and humility. There is also a deeper implication to this shift toward monitoring black holes as evolving systems. It blurs the line between astrophysics and experiment. Traditionally, experiments are controlled. Variables are isolated. Conditions are repeated. Black holes cannot be controlled. But if they exhibit recurring behavior, cycles, transitions, instabilities, then observing those patterns becomes a form of natural experiment. Nature runs the experiment. We watch. This reframes black holes from static endpoints into active laboratories, places where gravity, magnetism, and motion interact continuously, places where our theories are tested not once, but repeatedly. And that repetition is what makes refinement possible. Another subtle consequence of this new perspective is how it affects our interpretation of past observations. If black hole environments evolve, then images taken at different times may not be directly comparable unless their temporal context is understood. This means that historical data may need reanalysis, not to correct mistakes, but to reinterpret meaning. A feature once dismissed as noise might represent a transient state. A discrepancy once attributed to error might reflect real evolution. As black hole astronomy matures, its relationship with time deepens. Time is no longer just a coordinate. It is a variable of interest. This has philosophical implications as well. For much of physics, black holes were treated as timeless objects, defined by eternal equations. Now we are forced to confront their temporality. They exist in time. They respond to their environment. They change, not in their essence, but in their expression. This does not weaken our understanding of black holes. It enriches it. It reminds us that even the most extreme objects in the universe are part of ongoing processes. Nothing is truly frozen. Nothing is completely isolated. Everything participates. As observations continue, scientists expect surprises, not necessarily dramatic ones, but subtle ones. Shifts in polarization, variations in brightness, changes in symmetry. Each small deviation is a clue. Each clue narrows the range of explanations, and slowly, the mystery becomes less about whether something is happening and more about what kind of system the event horizon environment truly is. Is it quasi-stable, punctuated by rare reconfigurations? Is it inherently turbulent, always on the edge of chaos? Or does it follow patterns we have not yet recognized? These are not trivial distinctions. They determine how black holes influence galaxies, how jets are sustained, and how energy flows across cosmic scales. They also determine how confident we can be in our theories. In the coming years, black hole astronomy will likely shift from proof of concept to precision science, from showing that we can image an event horizon to understanding how that horizon's surroundings behave over time. This transition mirrors earlier moments in science. The first images of the moon revealed craters. Later observations revealed geology. The first spectra of stars revealed composition. Later observations revealed evolution. The first black hole image revealed a shadow. The next phase will reveal dynamics. And dynamics always complicates simple pictures. That complication is not a setback. It is progress. Because when nature behaves differently than expected, it is offering information, not confusion. The challenge is to listen carefully. As we move forward, the question is no longer whether the event horizon environment can change. It is how much it changes, how often, and why. In the next part, we will step beyond M87 star and ask a broader question. If this behavior is real, and if it is common, what does it mean for our understanding of black holes across the universe? Because a mystery at one horizon may be a universal feature waiting to be recognized. When the behavior near M87 star is placed into a wider cosmic context, its significance deepens, because M87 star is not special in kind. It is special in scale, and scale determines what we are able to see. If the environment near one supermassive black hole's event horizon is changing, then the most important question becomes unavoidable. Is this behavior unique or universal? To answer that, scientists must step beyond a single object and ask what black holes as a population are actually like. For much of modern astrophysics, black holes were treated as a class of objects defined by simplicity. Regardless of their mass, they were thought to behave according to the same rules, differing only in size and timescale. That assumption may still be true, but the observations are now forcing a refinement. Black holes may be simple in their internal description, but complex in their interaction with their surroundings. And that complexity may scale in ways we did not anticipate. Consider stellar mass black holes. These objects form when massive stars collapse, leaving behind a core only a few times more massive than the Sun. Near their event horizons, matter moves quickly. Magnetic fields reorganize rapidly. Jets flicker. Accretion disks fluctuate. In these systems, change is expected, but it is also difficult to resolve. Everything happens too fast. Any magnetic reconfiguration near the horizon unfolds in milliseconds or seconds. Even our fastest instruments struggle to track such motion directly. So for decades, the assumption was that supermassive black holes were simply the same phenomenon, slowed down. Larger mass means longer timescales, calmer evolution, greater stability. M87 star fit that expectation, until it didn't. The polarization changes now suggest that even at enormous mass, the region near the horizon may remain dynamic, not violently so, but persistently. This hints at a universality of behavior, not in the details, but in the nature of the system. Black hole edges may always exist in a state of tension between order and chaos. Gravity tries to enforce structure. Magnetism introduces flexibility. Plasma introduces turbulence. That combination may never fully settle. If this is true, then the classic picture of black holes as quiet sinks surrounded by smooth disks needs revision. They may be more like weather systems, large-scale stability punctuated by local instability, long-term equilibrium punctuated by short-term rearrangement. This would explain why the EHT observations appear surprising without being revolutionary. The event horizon itself remains intact, but the weather around it changes. Another important implication concerns the feedback between black holes and galaxies. Supermassive black holes are not passive residents of galactic centers. Their jets and outflows influence star formation, gas distribution, and galactic evolution. If the magnetic and plasma environment near the event horizon is dynamic, then the black hole's influence may fluctuate as well. Small changes near the horizon could cascade outward, subtly altering jet power or orientation over long periods. These effects would not necessarily be dramatic, but over millions of years, even subtle changes can shape galaxies. This introduces a new layer of complexity into models of cosmic evolution. Black holes may not just inject energy, they may modulate it. And that modulation may originate at the smallest scales we can observe. Another dimension of universality concerns black hole spin. Spin plays a central role in shaping the environment near the horizon. Faster spin enhances frame dragging. It strengthens the coupling between magnetic fields and space-time. M87 star is thought to be rapidly rotating. If polarization changes are linked to spin-driven effects, then similar behavior should be more pronounced in other rapidly spinning black holes. This opens a new observational strategy. By comparing black holes with different spins, scientists may be able to identify systematic patterns in horizon-adjacent behavior. Spin may not just determine jet power. It may determine how dynamic the edge environment is. This possibility is still speculative, but it is testable, and testability is what turns mystery into science. Another universal factor is accretion state. Black holes do not accrete matter at constant rates. They go through phases: quiet periods, active feeding, bursts. These phases affect disk structure, magnetic field strength, and plasma density. If the changes near M87 star reflect transitions between accretion states, then similar transitions should occur in other systems. The difference is detectability. For smaller black holes, the transitions are too fast to image directly. For larger ones, we can finally watch. This reframes supermassive black holes as time-lapse versions of a universal process. They allow us to slow down the universe, and slowing down the universe reveals structure. Another implication of universality concerns theoretical limits. If dynamic behavior near event horizons is common, then theories must accommodate variability, not just equilibrium solutions. This shifts emphasis away from steady-state models and toward time-dependent ones. In practice, this is difficult. Time-dependent relativistic simulations are computationally expensive. They require enormous resources and long runtimes, but necessity drives innovation. As observational evidence accumulates, theory must follow. This is how progress happens. Another subtle but important consequence is epistemological. For decades, black hole physics was dominated by thought experiments and mathematical proofs. Direct observation played a limited role. Now that we can observe the edge of a black hole, theory is no longer the sole arbiter. Data can surprise. This changes the culture of the field. Physicists accustomed to certainty must learn to live with ambiguity. Astrophysicists accustomed to indirect inference must confront direct constraints. This convergence is healthy. It forces humility. It reminds us that even our most elegant equations are approximations of reality, not replacements for it. Another universal lesson concerns the meaning of stability. Stability does not mean stillness. It means bounded change. A system can be stable and dynamic at the same time. The climate on Earth is stable, but weather changes daily. A star is stable, but plasma flows continuously. A black hole may be stable, but its surroundings may never stop rearranging. This reframing dissolves a false dichotomy. Black holes are not either static or chaotic. They are structured systems with dynamic components. Understanding that nuance is essential. It prevents overreaction to new data. It also prevents complacency, because dynamic systems can cross thresholds. The region near an event horizon may be stable today and unstable tomorrow, not because of external shocks, but because internal feedbacks accumulate. Whether such thresholds exist near black holes is unknown, but the possibility alone warrants attention. Another implication of universality touches on cosmic time. If black hole environments evolve, then the appearance of black holes at different cosmic epochs may differ systematically. Early universe black holes may have had different magnetic structures than those we see today. This could influence how jets behaved in the early universe and how galaxies evolved. Understanding horizon-adjacent dynamics is not just about black holes themselves. It is about cosmic history. Finally, universality reframes the emotional response to these discoveries. There is a temptation to treat unexpected behavior as alarming, but science thrives on such moments. They indicate that observation has outrun assumption, that nature is richer than our models, that learning is ongoing. The fact that scientists do not yet know why the environment near the event horizon is changing is not a weakness. It is a sign that we are finally asking the right questions. We are no longer content with silhouettes. We want motion, we want cause, we want mechanism, and those desires push science forward. As more black holes are imaged, patterns will emerge. Some will confirm expectations, some will challenge them. But the overall picture will sharpen. Black holes will move from being symbolic extremes to empirically grounded systems, and the event horizon will move from being a conceptual boundary to being a region whose behavior we can study, slowly, carefully, and with humility. In the next part, we will confront a final layer of this mystery. If the environment near the event horizon is dynamic and possibly chaotic, what does that mean for one of the most famous ideas in black hole physics? The idea that black holes erase information. Because at the edge of space-time, even old paradoxes may need to be reconsidered. For decades, one idea has haunted black hole physics more than any other: the idea that black holes destroy information. It began as a theoretical puzzle, almost philosophical in nature. According to quantum mechanics, information cannot be destroyed. The exact state of a system must, in principle, always be recoverable. But according to classical interpretations of black holes, anything that crosses the event horizon is lost forever. That tension became known as the black hole information paradox. For a long time, this paradox lived entirely in equations. It was a problem for theorists, not observers. The event horizon was assumed to be smooth, featureless, and inert. Whatever happened there was invisible and, for practical purposes, irrelevant to astronomy. But the recent observations are forcing a subtle shift, not because they solve the paradox, but because they change how we think about the boundary where the paradox lives. The environment near the event horizon is no longer an abstract concept. It is an observable region, one that appears to evolve, reorganize, and respond to physical processes. And that matters, because information does not disappear in isolation. It interacts with matter, fields, and radiation before ever reaching the horizon. If the region just outside the event horizon is dynamic, then the story of information loss may be more complicated than a simple crossing of an invisible line. To understand why, we need to clarify what physicists mean by information. Information is not memory or meaning. It is the complete description of a physical system: positions, velocities, quantum states. When matter falls toward a black hole, it carries information about its past. The paradox arises because classical black holes seem to erase that information, violating a fundamental rule of quantum physics. Over the years, many resolutions have been proposed. Some suggest information is encoded on the event horizon itself. Others propose it is carried away in subtle correlations in Hawking radiation. Still others suggest space-time itself must be modified. None of these ideas have been directly testable until now. Not because we can see information escaping, but because we can see the conditions under which information would be processed. The region near the event horizon is where infalling matter is stretched, heated, and magnetically entangled. It is where quantum fields interact with extreme curvature. It is where information becomes scrambled long before it is lost from view. The recent polarization changes hint that this scrambling environment is not static. Magnetic fields reorganize, plasma flows shift, light paths change. This suggests that the processing of information near the horizon may be time-dependent, not a one-time event, but an ongoing, evolving process. This does not mean information is escaping, but it does mean the boundary is more active than once thought. Some theoretical frameworks already anticipated this. In the holographic principle, information about a volume of space is encoded on its boundary. Applied to black holes, this suggests that the event horizon, or something extremely close to it, stores information about what falls in. If the boundary region is dynamic, then the way information is encoded may also be dynamic. Not static inscriptions, but evolving patterns. Another related idea is scrambling. Black holes are thought to be the fastest scramblers of information in the universe. Any information that approaches the horizon becomes rapidly mixed among all available degrees of freedom. If scrambling is happening in a dynamic environment where magnetic fields and plasma flows change over time, then the scrambling process itself may have structure. This opens the door to observational consequences, not direct retrieval of information, but indirect signatures in radiation, polarization, and variability. Again, caution is essential. No observation so far directly probes quantum gravity, but what we are seeing does challenge the notion that the horizon-adjacent region is inert. It is active, and activity implies interaction. Another layer of this discussion involves Hawking radiation. In theory, black holes slowly emit radiation due to quantum effects near the horizon. This radiation is extraordinarily weak for supermassive black holes, far too weak to detect directly. But Hawking radiation is generated precisely at the boundary where classical and quantum physics meet. If the classical environment near the horizon is dynamic, it raises subtle questions. Does that dynamism influence how quantum fluctuations behave? Does it affect how information is encoded in outgoing radiation? Does it change the timescale over which information could, in principle, be released? These are not questions we can answer observationally yet, but they are no longer purely abstract. They are grounded in a real, evolving environment. Another implication concerns the smoothness of the horizon. Some speculative theories suggest that the event horizon may not be perfectly smooth at the smallest scales. Instead, it might have structure, sometimes called quantum hair, or, in more extreme proposals, firewalls. The observations do not support such extreme ideas, but they do show that the region near the horizon is structured in ways we did not fully appreciate. This makes it harder to argue that everything near the horizon must be perfectly featureless. It does not imply drama. It implies nuance. There is also a psychological shift happening within the field. For years, discussions of information loss were dominated by thought experiments involving observers falling into black holes or hovering just above the horizon. Now, the focus is shifting outward, toward what can be measured, toward what light actually does near the horizon, toward how fields behave under extreme conditions. This shift grounds the paradox in empirical reality. Even if we cannot resolve it fully, we can constrain it. We can rule out some ideas. We can favor others. And over time, we can narrow the space of possibilities. Another important realization is that information loss, if it occurs, may not be a single event. It may be a process. Information may degrade gradually as matter approaches the horizon, scrambled, mixed, and dispersed among many degrees of freedom. By the time it crosses the horizon, the information may already be effectively inaccessible. In that sense, the horizon is not where information disappears. It is where disappearance becomes complete. If the environment near the horizon is changing, then the pathway to disappearance may vary over time. This could introduce variability in how information is processed, again, not observable directly, but conceptually important. It reframes the paradox from a sharp contradiction to a gradual transition. Another consequence of this view is humility. The information paradox may not have a single, elegant resolution. It may reflect the limits of applying human intuition to extreme regimes. Black holes operate at the intersection of theories that were never meant to coexist comfortably. Expecting clean answers may be unrealistic. What the new observations offer is not resolution, but constraint. They tell us that the horizon-adjacent region is not frozen, that whatever physics resolves, the paradox must accommodate dynamism, interaction, and evolution. Static pictures will not suffice. Finally, there is a broader philosophical implication. Black holes have long been symbols of finality, places where things end, disappear, and are erased. The evolving environment near the event horizon complicates that symbolism. It suggests that even at the edge of nothingness, processes continue, not inside the horizon, but right up against it. This does not soften the mystery, it deepens it, because it shows that the universe does not simplify at its extremes. It becomes more intricate, and that intricacy is observable. In the next part, we will step back one final time, not to seek answers, but to ask what this mystery ultimately represents. What does it mean that the most absolute boundary in physics is surrounded by complexity we are only beginning to understand? And what does that say about the limits of knowledge itself? That is where the story moves next. At some point, every scientific mystery stops being just a technical problem and starts becoming a mirror. The changing environment near the event horizon forces us into that moment, because the question is no longer only what is happening near black holes. It is also how far our way of knowing can reach. For most of human history, the universe was understood through patterns that felt stable. The stars returned each night. The planets followed predictable paths. Even when surprises appeared, they eventually settled into laws. Black holes disrupted that comfort. They introduced boundaries, regions where prediction fails not because of ignorance, but because of principle. The event horizon was the ultimate example, a place where physics itself draws a line and says, no further. And yet now, at that very boundary, we are seeing motion, not beyond the line, but right at its edge. This forces a philosophical recalibration. The event horizon was once treated as a static divider between knowable and unknowable, a clean separation between outside physics and inside mystery. The observations suggest something subtler. The boundary exists, but the approach to it is not simple. It is layered, structured, evolving. This challenges a deeply ingrained assumption in science, that ignorance lives only beyond horizons, not near them. In reality, the most interesting ignorance may live right at the boundary, where theories still apply, but only barely. That is where complexity thrives. Another implication is about models versus reality. Scientific models are built to simplify. They isolate variables, assume symmetry, and focus on dominant effects. This is not a flaw. It is the only way understanding is possible. But extreme environments punish simplification. Near an event horizon, no single effect dominates. Gravity is strong. Magnetism is intense. Plasma is turbulent. Relativity warps time and space. All of these interact simultaneously. When models fail here, it does not mean they are wrong. It means they are incomplete. An incompleteness at the edge of space-time is not surprising. What is surprising is that we can observe that incompleteness at all. This represents a shift in the philosophy of science itself. For centuries, observation followed theory. Telescopes confirmed predictions. Experiments validated equations. Black hole observation is reversing that order. We are now seeing things before we fully understand them. The data is leading. Theory is catching up. That is a rare and powerful moment in science. It is also uncomfortable because it means admitting uncertainty, not as a temporary gap, but as a persistent feature. Another philosophical consequence concerns the meaning of explanation. When scientists say, "We don't know why," it can sound like failure. But in this context, it is closer to honesty. The observed changes near the event horizon may have multiple overlapping causes: magnetic reconnection, turbulence, frame dragging, accretion variability, all acting together. There may not be a single, clean explanation. There may be a network of explanations. This challenges the expectation that nature always offers simple answers. Sometimes, nature offers systems whose behavior can be described, but not reduced. Weather is like this. Ecosystems are like this. The environment near a black hole may be like this too. Predictable in bounds, unpredictable in detail. Another layer of reflection involves human scale. Black holes operate on scales of mass, energy, and curvature far beyond everyday experience. Yet the changes being observed unfold over years, timescales familiar to human life. This convergence is strange. It means that cosmic processes we once thought timeless are now unfolding on human schedules. Not because black holes have changed, but because our ability to observe them has. We are witnessing a convergence between cosmic time and human time. That has emotional consequences. It makes the universe feel less distant, less frozen, more alive. Another philosophical shift concerns finality. Black holes were once symbols of irreversible endings. Matter falls in. Information is lost. Stories stop. The evolving horizon environment complicates that narrative, not because it denies finality, but because it reveals long preludes. The end is not sudden. It is preceded by a long process of transformation, scrambling, and interaction. This mirrors many natural processes. Death is preceded by change. Collapse is preceded by instability. The universe does not erase things instantly. It transforms them until erasure becomes unavoidable. This perspective softens the sharpness of paradoxes. It replaces binary thinking with gradients, and gradients are often where understanding lives. Another implication concerns epistemic humility. Black holes remind us that there are limits, not just to technology, but to conceptual frameworks. We may never have a complete description of what happens at or inside the event horizon, but completeness is not required for insight. Understanding how systems behave near their limits is often enough to reshape theory. We do not fully understand turbulence, yet we use fluid dynamics every day. We do not fully understand consciousness, yet neuroscience progresses. Black hole physics may follow a similar path. Practical understanding without ultimate resolution, and that may be sufficient. Another reflection emerges around progress itself. Scientific progress is often imagined as linear. Problems are solved, mysteries resolved, chapters closed. The event horizon resists closure. Each observation opens new questions. Each answer exposes deeper layers. This is not stagnation, it is depth. Some domains of nature are shallow. They yield quickly. Others are deep. They reward patience. Black holes are deep. They may remain deep forever. And that is not a weakness of science. It is a reminder of its scope. Another philosophical consequence is about meaning. Humans have always projected meaning onto black holes: fear, mystery, finality, power. The evolving edge forces a quieter interpretation. Black holes are not monsters. They are processes. They obey laws. They respond to conditions. They change. That does not make them less mysterious. It makes them more natural. And nature, at its extremes, is often more subtle than myth. There is also an ethical dimension to this shift. As science pushes closer to fundamental limits, it becomes important to communicate uncertainty responsibly. Sensationalism is tempting. The laws of physics are breaking, attracts attention, but it distorts reality. What is actually happening is more interesting and more honest. The laws are holding, but they are revealing complexity we did not anticipate. That distinction matters. It preserves trust. It respects the intelligence of the audience, and it honors the nature of discovery. Another important realization is that boundaries are rarely simple. In physics, boundaries often host the richest phenomena. The surface of a star is where fusion energy escapes. The boundary between atmosphere and space is where auroras form. The edge of a black hole may be similar, not a sharp cut, but a region, a transition, a place where different regimes meet. Understanding boundaries may be more important than understanding interiors, because boundaries are where interaction happens. The evolving event horizon environment suggests that the edge is not a point, but a zone of extreme physics, and zones can evolve. Finally, there is a quiet but profound implication about curiosity itself. Black holes were once purely theoretical. Then they became observable. Now they are becoming monitorable. This progression reflects something fundamental about human inquiry. We are drawn to edges, not because we expect easy answers, but because edges reveal the structure of understanding itself. When the edge shifts, our map must be redrawn. The changing environment near the event horizon is one such shift, not a collapse of knowledge, but an invitation. an invitation to refine theories, expand observations, and accept complexity. In the next and final part, we will bring the story to rest, not with resolution, but with perspective. We will ask what this mystery ultimately teaches us, not just about black holes, but about how science advances when it confronts the limits of what can be known. Because at the edge of space-time, we are also standing at the edge of understanding. As this mystery unfolds, it becomes clear that the changing environment near the event horizon is not an isolated anomaly, but part of a broader transformation in how black holes are studied, understood, and contextualized within science. For most of the 20th century, black holes were mathematical consequences. They emerged naturally from Einstein's equations, but they lived primarily on chalkboards and in thought experiments. Observational confirmation came slowly, indirectly, and often contentiously. Even when black holes were accepted as real, they remained abstract, invisible, defined by what they did rather than what they were. The ability to observe the region near an event horizon changed that relationship fundamentally. And now, the realization that this region evolves over time marks a second transformation, one that is quieter, but arguably more profound, because it forces scientists to abandon the idea that black holes are static reference points. They are not fixed anchors in space-time. They are evolving systems embedded in larger environments. This realization reshapes how evidence is interpreted. An image is no longer a final answer. It is a moment, a single frame in a longer story. And that shift has consequences not just for black hole physics, but for astronomy as a whole. Astronomy has traditionally relied on snapshots. We observe distant objects at one moment in time and infer their behavior across epochs. Stars evolve too slowly to watch directly. Galaxies change over millions of years. Black holes were thought to belong to that category, objects whose meaningful evolution was invisible on human timescales. The polarization changes challenge that assumption. They show that at least some aspects of black hole behavior unfold quickly enough to be observed. This blurs the line between astronomy and time domain science. Black holes are entering the same category as pulsars, variable stars, and supernova remnants, systems whose behavior must be tracked over time. That demands a different mindset. Instead of asking, what does a black hole look like? Scientists must ask, how does a black hole behave? Behavior implies causality. Behavior implies response. Behavior implies state. This reframing encourages new questions. Do black holes have preferred configurations? Do they transition between modes? Do they exhibit long-term cycles? These questions would have seemed strange a generation ago. Now they feel inevitable. Another important shift concerns interpretive caution. When an object is assumed to be static, deviations are often treated as noise or error. When variability is expected, deviations become signals. This change in expectation alters how data is filtered, modeled, and trusted. The EHT polarization data did not initially scream new physics. It whispered inconsistency. Only after careful comparison over time did that inconsistency become meaningful. This highlights a crucial lesson. Discovery often begins as discomfort, not as dramatic contradiction, but as subtle misalignment. Something does not quite fit. Something does not quite repeat. And instead of discarding the data, scientists sit with that discomfort. They test it, they re-observe, they hesitate. Only then do they speak. This process is slow, deliberate, and deeply human. It is also one of science's greatest strengths. Another implication of this evolving picture is interdisciplinary convergence. Understanding what is happening near the event horizon requires expertise from many domains: general relativity, plasma physics, magnetohydrodynamics, computational science, signal processing. No single discipline can dominate. This forces collaboration. It also forces translation between mathematical languages, conceptual frameworks, and methodological cultures. These translations are not trivial. They slow progress, but they also deepen it. When ideas survive translation across disciplines, they tend to be robust. The mystery near the event horizon is becoming a meeting ground, not just for data, but for perspectives. Another subtle but important consequence involves expectations of certainty. Modern science is often portrayed as a steady march toward definitive answers. In reality, many of the most interesting domains remain permanently open-ended. Black hole physics may be one of them. The changing environment near the horizon may never be reducible to a single explanation. It may resist closure. That does not mean understanding fails. It means understanding becomes probabilistic, contextual, and layered. Instead of asking, "What is happening?" scientists may need to ask, "What range of behaviors is possible under these conditions?" This is not a retreat. It is an adaptation. Complex systems require complex descriptions. Another dimension of this shift is educational. Textbooks tend to present black holes as finished topics, defined, classified, understood. The new observations disrupt that narrative. They reveal that black hole science is not a closed chapter, but a developing field. This has consequences for how future scientists are trained. They must learn not just equations, but uncertainty. Not just results, but process. Not just answers, but how to live with unanswered questions. This is especially important at the boundaries of knowledge, because boundaries are where misconceptions thrive. Another implication concerns public understanding. Black holes occupy a unique place in popular imagination. They are symbols of mystery, danger, and ultimate unknowability. The evolving edge complicates that symbolism. It replaces the idea of a singular mystery with a layered one. Not a single question with a dramatic answer, but many questions, each with partial, evolving answers. Communicating that complexity without losing engagement is a challenge, but it is also an opportunity. Because real science is more interesting than myth. It is slower, more careful, more honest. Another consequence of this discovery is its effect on future mission priorities. Funding agencies and observatories must decide what questions are worth pursuing. The realization that black hole environments evolve gives new urgency to long-term monitoring. It strengthens the case for sustained observation rather than one-off achievements. It also justifies investments in infrastructure that prioritizes continuity. Science advances not just through breakthroughs, but through persistence. Another philosophical implication emerges around the nature of limits. The event horizon was once seen as an absolute epistemic boundary. We could approach it, but never learn anything about what lies beyond. That boundary remains, but the richness of physics just outside it suggests that limits are not always where we think they are. Sometimes the most informative region is not beyond the boundary, but just before it. This insight may apply beyond black holes. In many domains, extremes reveal structure not visible in moderate regimes. The edge of stability, the onset of chaos, the threshold of collapse, these are often the most instructive places to look. Black holes may be teaching us a general lesson about inquiry. Another layer of reflection concerns patience. The changes near the event horizon unfold over years. Understanding them may take decades. This demands a kind of scientific patience that is increasingly rare in a world driven by rapid results. But some questions cannot be rushed. They require long baselines, repeated measurement, and the willingness to wait. Black hole science rewards that patience. It also demands it. Finally, there is a quiet emotional shift that accompanies this work. For scientists who have spent their careers studying black holes as abstract entities, seeing their behavior change over time is unsettling. But it is also exhilarating. It feels like meeting an old concept as a living thing, something that responds, something that surprises. That feeling, the mixture of discomfort and wonder, is a hallmark of genuine discovery. The event horizon is no longer just a theoretical boundary. It is part of an evolving story, a story that we have only just begun to read. In the final part, we will step back one last time, not to resolve the mystery, but to ask what it ultimately signifies. What does it mean that the most extreme boundary in physics is surrounded by behavior we did not anticipate? And what does that tell us about the future of knowledge when observation reaches the edge of what theory can explain? That is where the journey concludes. There is a temptation when reaching the end of a scientific mystery to search for closure, a final answer, a definitive explanation, a line that can be drawn under uncertainty. But some discoveries resist that instinct, not because they are unsolvable, but because they reveal something deeper about how understanding itself works. The changing environment near the event horizon belongs to that category. It does not conclude a story. It reframes it. For much of modern physics, black holes were treated as ultimate conclusions, endpoints of gravitational collapse, places where motion stops, time freezes, and information disappears behind a permanent veil. They were symbols of finality. What the recent observations suggest is almost the opposite. Not that black holes are less extreme, but that extremity does not imply stillness. At the edge of space-time, processes continue. They reorganize, they fluctuate, they evolve. The event horizon remains absolute, but the universe does not fall silent at its boundary. This realization subtly changes how we think about limits. In science, limits are often imagined as walls, places where progress halts. But the event horizon is not a wall. It is a boundary condition, and boundary conditions are often where the richest behavior emerges. In mathematics, boundaries define solutions. In physics, boundaries host transitions. In nature, boundaries are where systems interact. The edge of a black hole is no exception. The evolving polarization patterns, the shifting magnetic structures, the dynamic plasma flows, all of these suggest that the most interesting physics may not lie beyond the horizon, but right up against it. This does not diminish the mystery of what lies inside. It contextualizes it. It shows that ignorance is not a void. It is surrounded by structure. Another lesson emerging from this story concerns the humility of explanation. Science often advances by replacing mystery with mechanism, but some domains do not yield to clean reduction. They demand layered understanding. The event horizon environment may be such a domain. There may be no single cause for the observed changes. Instead, there may be interacting processes whose combined behavior cannot be simplified without loss. This is not a failure of science. It is a recognition of complexity. Complex systems are not less scientific. They are more demanding. They require probabilistic thinking. They require long-term observation. They require acceptance that prediction may be bounded. Black holes may be teaching us that the universe does not always reward simplicity. Sometimes it rewards patience. Another profound implication of this discovery lies in its effect on scientific confidence. Confidence in physics does not come from believing we have final answers. It comes from trusting the methods that lead us closer to truth. The fact that scientists are willing to say, "We don't know why," is not weakness. It is strength. It signals that observation is being taken seriously, even when it challenges comfortable assumptions. In an era where certainty is often demanded, black hole science models a different virtue: intellectual honesty. This honesty is essential at the frontiers of knowledge, because frontiers are where error is most likely and humility most necessary. Another takeaway from this story is about continuity. Black holes were once thought to represent breaks in the fabric of understanding, places where laws stop applying. Instead, they may represent continuity pushed to extremes. The same physical principles govern plasma, magnetism, and motion near a black hole as elsewhere. What changes is intensity. Curvature increases. Energy densities rise. Timescales stretch or compress. Under those conditions, familiar laws produce unfamiliar behavior. The universe does not invent new rules at the edge. It explores the full implications of existing ones. That is both reassuring and unsettling. Reassuring because it suggests coherence. Unsettling because it means complexity is not an exception. It is a consequence. Another reflection concerns the role of observation in shaping theory. Theories of black holes existed long before images did. They were mathematically consistent and conceptually elegant. But elegance is not completeness. Observation tests not just predictions, but assumptions. The assumption that the environment near the event horizon is static was reasonable. It was also wrong. Not catastrophically wrong, but incomplete. And that incompleteness matters, because it reminds us that theory without observation is fragile, especially at extremes. The EHT did more than image a black hole. It rebalanced the relationship between mathematics and measurement. It reminded us that nature is the final arbiter. Another subtle but important implication is how we define understanding. Do we understand a system when we can describe its average behavior? Or do we require the ability to predict its detailed evolution? In many domains, climate, ecosystems, turbulence, we accept partial understanding. We model trends, not exact outcomes. Black hole environments may belong to that category. We may learn the range of possible behaviors near an event horizon without predicting each transition. And that may be enough. Understanding does not require omniscience. It requires context. Another lesson is about the future of discovery. The changing event horizon environment did not announce itself dramatically. It emerged slowly, through careful comparison, over years. This suggests that some of the most important discoveries ahead may not come from new theories or new instruments alone, but from persistence, from returning to the same objects again and again, from asking not what is there, but what is changing. This mindset will shape the next generation of astronomy. Black holes will be watched, not just imaged, tracked, not just captured. This approach will likely reveal other surprises, not only near horizons, but across the universe. Because time reveals what space alone cannot. Another reflection concerns meaning beyond science. Black holes have always inspired metaphor. They represent the unknown, the final boundary, the collapse of certainty. The evolving edge adds nuance to that metaphor. It suggests that even where knowledge fails, structure remains. That even at limits, there is process. That finality is often preceded by long, complex transitions. This resonates beyond physics. In many areas of human experience, endings are not abrupt. They unfold, they reorganize, they leave traces. Black holes may be cosmic analogues of that truth. Finally, there is a quiet but powerful conclusion to draw. The event horizon is not changing in violation of physics, but our relationship to it is changing. We are no longer content to define it abstractly. We want to understand its neighborhood, its dynamics, its role in larger systems. That curiosity marks a turning point. It signals that black hole physics has matured from speculation to observation, from static models to evolving narratives. The mystery remains, but it is now a shared space between data and theory, between humility and ambition, between what we know and what we are willing to admit we do not. That balance is the hallmark of good science, and it is fitting that such a balance emerges at the edge of space-time itself. Because if the universe has taught us anything through black holes, it is this: the most absolute boundaries do not end inquiry. They define where inquiry becomes most meaningful. And at the event horizon, quietly, slowly, without spectacle, that inquiry continues. As the story draws closer to its end, one final realization comes into focus, one that quietly reshapes everything that came before. The changing environment near the event horizon is not just a discovery about black holes. It is a discovery about how knowledge progresses when it reaches its natural limits. For centuries, science advanced by conquering unknowns. Each mystery solved seemed to shrink the map of ignorance. The expectation, often unspoken, was that understanding would eventually close every gap. Black holes were supposed to be the final gap, a place where physics itself admitted defeat. And yet, what we are witnessing now is not defeat, but transformation. The event horizon remains an ultimate boundary. Nothing we have learned allows us to see past it. Nothing observed contradicts that rule. But what has changed is our appreciation of what surrounds that boundary. The region just outside the horizon is not a featureless waiting room before oblivion. It is an active, structured, evolving domain, one that responds to forces, reorganizes itself, and carries memory of what passes through it. This realization reframes the role of limits in science. Limits are not empty, they are fertile. They are where theories stretch, interact, and sometimes reveal assumptions we didn't realize we were making. The event horizon, long treated as a conceptual endpoint, is becoming a site of inquiry in its own right, and that shift has consequences far beyond black hole physics. One of the deepest lessons emerging from this work is about expectation. For decades, scientists expected the environment near a supermassive black hole to be relatively calm on human timescales. That expectation shaped models, observing strategies, and interpretations. The data quietly disagreed, not dramatically, not all at once, but persistently. This is how scientific revolutions usually begin, not with contradiction, but with tension. Data that refuses to sit comfortably within existing frameworks. What makes this moment important is not that expectations were wrong, but that they were reasonable. And reasonableness is exactly what makes revision meaningful. Another important realization concerns the difference between simplicity and reduction. Black holes are often described as simple objects, and in a strict sense, they are. They can be fully described by mass, spin, and charge. But that description applies to the black hole itself, not to its surroundings. The mistake was assuming simplicity extends outward. The environment near an event horizon is governed by simple laws applied under extreme conditions. That combination does not produce simplicity. It produces richness, and richness demands careful, layered understanding. This distinction matters because it preserves the integrity of theory while acknowledging observational complexity. Einstein's equations still hold, but their consequences, when combined with magnetism, plasma, and rotation, are more elaborate than early intuition suggested. Another lesson lies in the role of patience. The changes observed near M87 star did not appear overnight. They emerged through years of observation, careful calibration, repeated analysis, and restraint in interpretation. In an age of rapid results and instant conclusions, this stands out. It reminds us that some truths are slow, not because they resist discovery, but because they require time to reveal themselves. Black holes operate on cosmic scales, but understanding them still requires human-scale patience. That patience is not passive, it is active attention. Another insight concerns how uncertainty should be communicated. There is a temptation, especially with dramatic topics like black holes, to frame uncertainty as crisis. The laws of physics are breaking. Everything we know is wrong. These narratives attract attention, but they misrepresent reality. What is happening near the event horizon is more subtle and more interesting. The laws are not breaking. They are being tested in regimes where their full implications are still unfolding. That distinction matters deeply. It preserves trust in science. It encourages curiosity rather than fear. It acknowledges mystery without manufacturing alarm. Another implication of this work concerns future generations of scientists. Students entering astrophysics today are inheriting a field that is no longer dominated by abstract thought experiments alone. They are inheriting real data from the edge of spacetime. This changes how the field is taught, learned, and imagined. Black hole physics is no longer a speculative frontier. It is an empirical one. That shift will shape how problems are framed, how models are built, how success is defined. Another subtle but profound consequence is the way this discovery reshapes scientific identity. Physicists have long been associated with certainty, precise equations, exact predictions, definitive answers. The changing event horizon environment reminds us that certainty is not the goal. Understanding is. And understanding can coexist with uncertainty. It can even depend on it. Accepting that some systems resist complete prediction does not weaken science. It matures it. It aligns expectations with reality. Another lesson emerges around scale and perspective. From a cosmic viewpoint, the changes observed near M87 star are tiny fluctuations in a vast system. From a human viewpoint, they are monumental because they occur at a boundary once thought unreachable. Perspective matters. The same phenomenon can be trivial or profound depending on context. Science advances by learning which contexts matter. The event horizon sits at one of those contexts. Another realization concerns the continuity of inquiry. There will not be a single paper, observation, or theory that resolves this mystery completely. Progress will come through accumulation, through improved instruments, through longer baselines, through better synthesis of theory and data. This is not a flaw. It is the normal rhythm of deep science. The deeper the question, the slower the answer unfolds. Finally, there is a quiet, almost poetic truth embedded in this story. Black holes were once symbols of silence, places where information, matter, and meaning vanished without trace. The changing environment near the event horizon suggests something different. Not that black holes speak, but that they respond. They carry signatures of interaction. They leave patterns. They reveal structure at the edge of disappearance. That is not a solution to every paradox, but it is a reminder that nature rarely conforms to our metaphors. It exceeds them. As we stand at the threshold of this mystery, one thing is clear. The event horizon is no longer just a line in an equation. It is a region we can study, a boundary we can monitor, a frontier where physics is still alive. In the final part, we will bring this journey to a close, not by resolving the mystery, but by placing it where it belongs, within the long arc of human curiosity, within the story of how we approach the unknown, and within the understanding that some boundaries are not meant to be crossed, but to be understood from the edge. In the end, the story of the changing event horizon is not a story about failure, danger, or broken laws. It is a story about arrival at a place science had pointed toward for over a century, but never truly reached. Einstein's equations told us black holes must exist. They described event horizons with mathematical precision. But for most of that history, the horizon was an abstraction, an invisible surface inferred from motion, gravity, and theory. Now, for the first time, humanity is not merely inferring the edge of a black hole. We are watching its neighborhood. And what we see there is not silence. It is motion. That realization marks a turning point in how we understand extreme physics, not because the event horizon itself has changed, but because our relationship to it has. For generations, black holes represented a conceptual endpoint, the place where prediction stops, where information disappears, where inquiry must turn back. The recent observations quietly overturn that framing. The event horizon remains an absolute boundary, but the region surrounding it is rich, structured, and alive with process. This distinction matters. It preserves the integrity of physics while expanding its reach. It tells us that knowledge does not stop at boundaries. It gathers around them. The changes observed near the horizon do not demand new laws of physics. They demand new patience, new observational strategies, new ways of thinking about systems that are stable yet dynamic, and perhaps most importantly, new humility. Humility to accept that some of nature's most profound truths reveal themselves slowly, not in dramatic breaks, but in subtle shifts, not in contradictions, but in complications. Black hole science is entering a mature phase, no longer content with asking whether black holes exist, no longer satisfied with silhouettes. It now asks how black holes behave as part of the universe's ongoing story. This shift has broader implications than it might seem. It challenges the idea that ultimate boundaries are uninformative. It suggests that even where access is denied, interaction persists. That even when a door is closed, the frame around it carries marks. The event horizon is such a frame, and those marks, encoded in light, polarization, and structure, are now within reach of observation. Another lesson emerging from this journey is about scale. Black holes are often described as cosmic monsters, far removed from human experience. Yet the changes being observed unfold on timescales we can relate to, years, not eons. This convergence is remarkable. It means the universe is not always indifferent to our scale. Sometimes it aligns with it, and when it does, it offers rare opportunities. The opportunity to watch processes once thought timeless, the opportunity to test ideas once thought untouchable, the opportunity to learn not just what the universe is, but how it changes. This is not a small thing. It marks a shift from static cosmology to dynamic cosmology, from frozen images to evolving systems, from abstraction to behavior. And that shift will echo across astronomy in the years to come. There is also a quieter, deeper implication. The changing environment near the event horizon reminds us that mystery is not an enemy of science. It is its companion. Mystery signals where understanding ends, not as a defeat, but as a guide. It tells us where to look next, where to refine instruments, where to revisit assumptions, where to listen more carefully to what nature is saying. The event horizon is not revealing its secrets easily, but it is revealing enough to keep inquiry alive. And that may be the most important outcome of all. This story does not resolve the information paradox. It does not rewrite general relativity. It does not unveil quantum gravity. What it does is more subtle and more powerful. It anchors those questions in reality. It reminds us that even the deepest theoretical puzzles are connected to observable phenomena, that equations are not detached from the universe. They describe it. And when the universe behaves in unexpected ways, the equations must grow, not collapse. Another profound takeaway concerns how science advances at its frontiers. Progress here is not linear. It is iterative. Observation informs theory. Theory refines observation. Misalignments appear. Understanding deepens. This cycle repeats. The changing event horizon environment is one turn of that cycle, not the end, not the beginning, but a meaningful step forward. There will be future observations, better resolution, more frequent monitoring, perhaps entirely new techniques. Each will add detail, each will narrow uncertainty, each will reveal new questions. This is not an infinite regress. It is an expansion of perspective, and perspective is what science ultimately offers. Finally, there is a human dimension to this story. For all the complexity of black holes, for all the mathematics and machinery, the act of discovery remains deeply human. It involves curiosity, doubt, patience, the willingness to say we don't know, and mean it as an invitation, not a confession. Standing at the edge of a black hole, we are also standing at the edge of understanding, not peering into darkness expecting answers, but observing carefully, letting patterns emerge, and allowing nature to teach us on its own terms. That posture, quiet, attentive, humble, is the true lesson of this discovery. The event horizon is changing, not in violation of physics, but in revelation of complexity. And scientists don't yet know why, but they know something else. They know that the universe is still capable of surprise, even at its most extreme boundaries. And as long as that remains true, the pursuit of understanding will continue. Not beyond the horizon, but right up against it, where the known meets the unknown, and where curiosity finds its most enduring home.